So what we've been working on is this really important circle. And in this very important circle, we have these tick marks that go around, these angles in standard position. We have things labeled that are in degrees. We have things labeled that are in radians. We should be able to do this relatively well at this point. So let's just recap. If you start right over here, we hit 0 degrees. If we go all the way around this circle, that's also equivalent to 360 degrees. Halfway between 0 and 360, we have 180 degrees. Halfway between 0 and 180 degrees, there's 90 degrees. And halfway between 0 and 90 degrees is 45 degrees. Then we can go around and count by increments of 45. 45, 90, 135, 180, 225, 270, 315, 360. If that's a little bit too hard for you to do, which it really might be, remember that you can add from 45, 100, and take away 10. Because if between this spot and this spot's 90, because it's two 45s, well, if I add 45 and 45, I'm really adding 90. And adding 90 is the same as adding 100 and taking away 10. 45 plus 100 is 145. Take away 10, 135. 135 plus 100 is 235. Take away 10, 225. Plus 100, 325, but take away 10, 315. Now, if I want angles bigger than 360, I'm going to have to keep adding 45 if I wanted to go around and round and find out where they land. And you'll understand why we might need to do this later. And if I wanted to go negative 45 degrees, negative 90, negative 135, negative 180, negative 225, negative 270, negative 315, negative 360, or even more negative than that, I would have to just continue. Degrees are a little bit difficult because the numbers get pretty big and adding gets difficult, and it's very easy to lose track of where things are. Now, we also put onto this circle increments of a different value. We put on increments of 30. 30 will overlap the 45 increments at 90 because that is a common multiple. Count by 30s, which are a sixth of 180 because it takes 6 30s to make 180. 30, 60, 90. 120, 150, 180. Sometimes it's easier to go backwards from 180 to 150 and 120, but you choose what works for you. Continue. 210, another important thing. This tick mark does not go in the middle of 180 and 225. It's actually a little bit closer to 225 degrees. 240, 270. In fact, if I counted by 15s, you would hit 285. Another 15 would put us at 300, which is 2 15s make a 30. 315. Another 15 would actually put us at 330, but that's the same as adding 30 to 300. 345, 360. So there's really these other little tick marks in here. If we were to count by 15 degrees, if that helps you understand the spacing of all of this, that's not a bad thing to understand. Those are the degree measures. We also learned another type of measurement referred to as radians. You should know how big 1 radian is at this point. 1 radian is equivalent to the angle measure of an angle where the radius and the arc length are equal. So 1 radian is slightly less than 60 degrees. It's 59 point something. But that's very difficult to mark up on here because 3 radians would be less than 180 degrees, some random spot over here, and we're not really too crazy about this. However, we also know that 1 full revolution is equal to 2 pi radians. So 0 radians, and radians has no units. 360 is 2 pi radians. Halfway between 0 and 2 pi is pi radians. Halfway between 0 radians and pi radians. What's halfway between 0 and 1 of something? Well, half of something, so pi over 2. What's halfway between 0 of something, 0 radians, and pi over 2 radians? Half of a half is a quarter, pi over 4. Just like counting by 45s, we're going to count by pi over 4s. 1 pi over 4, 2 pi over 4, but we reduce because we're real good. 3 pi over 4. 4 pi over 4 is a checkpoint. That's pi. 5 pi over 4. Now, if you think about this, this is more than 1 pi because our numerator is bigger than our denominator, 5 pi over 4. How many pi over 4s do you have? 5 of them. 4 pi over 4 is 1 whole pi, more than 1 pi, right? After 5 pi over 4 is 6 pi over 4, which reduces to 3 pi over 2. You should also know that 3 halves is 1.5, so this is 1.5 pi's. Because again, pi is half the circle. 5 pi over 4, 6 pi over 4, 315 is 7 pi over 4, 8 pi over 4. Now, radians are actually much easier for us to kind of keep going around and find where something like 9 pi over 4, 10 pi over 4, 11 pi over 4, 12 pi over 4, which is 3 pi, 13 pi over 4, 14 pi over 4, which is actually 7 pi over 2, 15 pi over 4, 16 pi over 4, which is 4 pi, and so on. It's much easier to find out where they land, especially when we have increments of 30 and 60. So basically, you could tell yourself that anything over 4 will land in the middle of a quadrant. Now, 30 degrees, we said, was 1/6 of 180. It's a 1/6 of half the circle. Not a 1/6 of the circle, but pi is half the circle. So 30 degrees is 1/6 of pi, or you could call that pi over 6. So if we start here, here we have, let me lower that. There we go. If this is 0 pi out of 6, 1 pi over 6, 2 pi over 6, reduce that, okay? Pi over 3. 3 pi over 6, which is pi over 2. 4 pi over 6, which is 2 pi over 3. 5 pi over 6. Remember, we're counting by 30 degrees, just using radians. 6 pi over 6, 7 pi over 6. Here we are again, where my numerator, 7, is larger than my denominator, 6. So it's more than 1 whole pi, because 6 pi over 6 is 1 pi. 8 pi over 6, which is 4 pi over 3. 9 pi over 6, which is 3 pi over 2. 10 pi over 6, which is 5 pi over 3. And 11 pi over 6. Does anyone else do that where you write 11 pi over 6 and you just write 11 and want to go to the denominator because the pi symbol has that, 11 motion? Just me? Okay. 11 pi over 6 and 12 pi over 6. If I wanted to know, well, where is 23 pi over 6? Well, if it has a 6 in the denominator, 23 pi over 6, and it doesn't reduce, something I know is it's going to land at the tick marks that are closest to the x-axis. I'm about to give you some golden advice right now. Because you're using radians much more than degrees from this point forward, it's really important that we know where these land. Anything over 6, the word 6 ends with an X. So the angles over 6 are going to land closer to the x-axis. Do you see? They are the ones that are going to be closest to the x-axis. And then the ones that have a 3 in the denominator, when I was learning this in high school and I always came up with some weird way to remember stuff, I said any amount of pi over 3, tall and skinny like a tree. So the angles that are over 3, see them right here, are the ones that are tall and skinny like a tree. So there, that's the blue tree. Okay, so you need to know where those are. And then the 4s, I just think like a perfect 4-sided figure, all sides and angles are the same. That makes a square. And if you connect the dots of the angles over 4, it makes a perfect square. Even amounts of pi are going to land on the right. Odd amounts of pi are on the left. And then the pi over 2s are on top and bottom. I don't want to overwhelm us with all this, but now, what is the point of all of this? Get it? Point, because you have to put the points on here too. The points are the ordered pairs that we have on this circle. This spot right here is the origin. We said that this circle has a radius of 1. Why? Why does this circle have a radius of 1? There is a reason. The reason we have a radius of 1 has to do with a couple things. Do you remember in your elementary school, you might have had one of those black and white composition notebooks? And in the back of those composition notebooks, you had those tables that had the numbers, say, 0, 1, 2, 3, 4, 5, maybe it went to like 15. And then this way, 1, 2, 3, 4, whatever. And I don't remember exactly. It might, maybe did it have 0 on both sides? I don't think so. Then what you could do is in the table, it was like boxed out. If you did 1, 1, over here, you'd get 1. Here you'd get 2. But here, I'm not going to fill in all of them, you'd get 4. Here you would get 6. Say you did this spot would be 20. And the table basically was doing your times tables, your multiplication table. So it was like if you multiply this number by this number, your answer is where they cross, right? And that worked for times tables because really there's no repetition, there's no pattern, it's not periodic, right? However, trigonometry is periodic. Trigonometry deals with angles, but angles from 0 to 360 covers all the angles we really are going to have different answers for. As soon as you pass 360, you're going to repeat a cycle. Repeat, repeat, repeat forever and ever and ever. So you wouldn't put this in a table. Same with going with negative angles. You don't want to find your trigonometric ratios. This is why we reviewed SOHCAHTOA as well. You wouldn't put these in a table because the angles that you would take the sine, cosine, or tangent of would just go on forever and your table would never end. Similar to the concept of time. So it's not like we come up with a new clock every single day, right? Those clocks on the wall, not digital clocks, okay? The clocks on the wall that are circular, we have the same set of numbers that we pass every day, so we don't make a new clock. We just put it on a circle since the answers repeat themselves over and over and over. Depending on how you learned about imaginary numbers, I know when I teach imaginary numbers, I sort of teach the I wheel. I know some people learn the I chart. The reason I teach it on a wheel is because imaginary numbers, similar to trigonometry, repeat themselves. So I always say to myself, I sounds like Y. So the I axis, the imaginary axis, is on the Y axis. So up here we have positive I and negative I. And then we'll also have 1 at the positive X and negative 1. Here is I to the first power, I to the second power, I to the third, I to the fourth. but every 4 it repeats. So I to the 5th, 6th, 7th, 8th, I to the 9th power, I to the 10th, 11th, and 12th. Why would I make a list going on and on forever when something repeats itself? So again, I to the 1, I to the 2, I to the 3, I to the 4, and then I just repeat one more, comma, I to the 5, I to the 6, I to the 7, I to the 8th. Once you have that, it really explains itself and you know it's cyclic and repeats itself over and over. Now, we have these ordered pairs that we put on the circle. Over here, with this radius of 1, we have the point 1, 0, representing this spot right over here. This was the ordered pair over a lot, up a little. A lot is square root of 3 over 2. Up a little is 1/2. Here at 45 over medium, up medium. Medium, medium is rad 2 over 2, rad 2 over 2. Now I'm obviously squeezing right now. At 60, we move over a little and up a lot. So this one, we had the ordered pair a little, which is 1/2, comma a lot, which is rad 3 over 2. At this top spot right here, we go over 0 and up 1. Here, I'm not going to label because it's these same ordered pairs, but left, up, left, up, left, up. This one is -1, comma 0. Down here is 0, comma -1. Now, if for some reason I needed you to tell me one of the trig ratios of 30 degrees. We went over the trig ratios, so, ka, toa, that you learned in geometry. The sine of an angle is equal to the opposite over hypotenuse. The nice thing about making the radius of this circle 1 means that every triangle I make in here from any of these points, by dropping an altitude to the x-axis or pulling up an altitude to the x-axis, every single triangle will have a hypotenuse of 1. Since sine and cosine are going to be the main 2 trig ratios, they're kind of like the Adam and Eve of this, okay? They're like the top of the family tree, and the other things that we do kind of come from sine and cosine. Sine has hypotenuse in the denominator, and so does cosine. By hypotenuse being 1, it actually saves you a step. How many times do you really write over 1? We don't, right? Unless you're going to do another step like finding a common denominator. So the sine of 30 degrees, or the sine of pi over 6, opposite over hypotenuse, this side is 1/2. The hypotenuse is 1, so I don't need to do anything. So the sine of pi over 6 is the y value of the ordered pair on the unit circle. That means that if this is true, you can take the sine, cosine, and tangent of 0 degrees, which normally you couldn't draw a triangle for. You could now take the sine of 90 degrees, which we couldn't do before either, because 90 is the angle that is opposite from the hypotenuse, and that wouldn't have made sense. We could also take the sine or cosine of angles greater than 180, but there's only 180 degrees in a triangle. You could take the sine of angles between 180 and 360, bigger than 360, of negative angles. So what you're going to do, to get the sine of an angle, you're going to give the y value on the unit circle. It's not on any circle, only the unit circle. Unit means 1 unit for the hypotenuse. So what if I asked you, what is the sine of negative 2 pi over 3. Oh, that didn't write very well, did it? I'm going to go right here. Sine of negative 2 pi over 3. There was a piece of Scotch tape, so it was too shiny. If I ask you for this, you would go here. Some people like to change it to 6. We will elaborate on this more later, but if you did, change it to a 6 denominator because maybe you're getting good at counting by the increments of 6. Remember that negative means counterclockwise. So, I'm sorry, negative means clockwise. 1 pi over 6, but negative 2 pi over 6, negative 3 pi over 6, negative 4 pi over 6. That's this, negative 4 pi over 6. Sine is the y value. Over a little, but down a lot. The y value is how far down. What's a lot? Negative, because down, square root of 3 over 2. Negative radical 3 over 2. Cosine. Cosine is adjacent over hypotenuse. What if I asked for the cosine of 135 degrees? Cosine of 135 degrees. Well, you wouldn't have a 135 degree angle inside of a right triangle. That wouldn't make sense. But with the unit circle, you can do this. Now, you connect your triangle down to the x-axis, and you're going to really refer to this triangle here. This is called your reference triangle. This is called a reference angle. Again, we'll get nitty-gritty later. But if I ask you for the cosine of 135 degrees, that's going to be adjacent. So the adjacent side is always here next to this angle, the reference angle. It's always against the x-axis, and then the opposite is always going to be out here. Adjacent over hypotenuse. But since the hypotenuse is 1 in a unit circle, it makes it easy. So my cosine of 135 degrees is really just adjacent, and 135 being in the middle is medium. Medium. So the cosine of 135 degrees equals square root 2 over 2, but we went to the left. So that changes our answer because now it's negative. I'm going to go over a couple more before we call it a day. What is the sine of 330 degrees? Now, if you have your circle in front of you with your ordered pairs labeled all the way around it, it's probably going to be the fastest way for you to learn right now. But the way I would do it, I know 330 is really only 30 degrees away from 360, so it's the one closer to the x-axis. So if it's close to the x-axis, it means I move over a lot and down a little. Sine is the y value on the unit circle. Down a little is negative 1/2. X, y on the unit circle, the x value is cosine of your angle, and the y value is the sine of your angle. Big information here, okay? So alphabetical order x, y, cosine, sine. Sine, y, assonance like in poetry where they kind of sound alike in the word, you know. What about cosine of negative 5 pi over 3? Negative 5 pi over 3, well, here's positive 5 pi over 3. I went all the way around. I went 3 quadrants and then pi over 3 more. But if it's negative, I got to go 1, 2, 3 quadrants and pi over 3 more. Negative 5 pi over 3 will land right there. Cosine is the x value. I went over a little, up a lot. Cosine's x, over a little. So the cosine is 1/2. The way I'm doing it is so that you can do this in your head and not look at the circle anymore. You're not going to look at the circle forever. You're going to do these in your head. How about the sine of 17 pi over 4? That's not on the unit circle. That means you have to go around more than just one full revolution. If you didn't have the circle in front of you, 4 is the middle one. 1 pi over 4, 2, 3, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Now continue. 9, 10, 11 pi over 4, 12, 13 pi over 4, 14, 15, 16, 17 pi over 4 is coterminal to this spot right here. I'm in quadrant 1, meaning I move over a positive amount, up a positive amount. The pi over 4s are my mediums, over medium, up medium. The sign is the y value. The answer is square root 2 over 2. What is the cosine of 22 pi? Cosine's your x value, your adjacent, how far over you're going, and with direction. 0 pi, 1 pi, 2 pi. I gave you a hint before. All of the odd increments of pi land here and evens land here. So I don't have to keep going. 22 pi's right there. What's the cosine right there? Positive 1, because it's the x value. I'm going to give you more problems like this to practice. You're going to use your circle, but try to get yourself off the circle. You're weaning yourself off to find the sines and cosines of various degree measures, radian measures, both positive, negative, and even greater than 1 revolution, or even maybe negative more than 1 revolution. You'll just have to keep counting around. I hope this helps, and good luck.